Hello, I thought I'd do a follow-up to the rubidium frequency standard that hack that I done the other day. I had so many comments about it, and there was a few and questions and suggestions and guidance even, and I thought I would cover some of those points off, because one of the questions that got asked is, or got asked quite a lot, there was quite a lot of thought and opinion, is: does it need a heatsink? Should you have a heatsink on the rubidium standard? Does it cool it down too much and therefore it will draw more current to try and warm it back up again? And there's kind of mixed feelings about it, and people are suggesting that perhaps, or some people are suggesting perhaps that it's meant to run at that high temperature. And the fact is, I don't think it is. It's not really clear in the manuals. I have had a look at the manuals now, although someone said that actually they should be the manual should make it clear, or does make it clear, that they need heat sinking. But if we just talk about them just for a second, the construction of these, inside here you've got a physics package, and that package has got two MOSFET transistors soldered to it, or glued to it, or welded to it, and that heats it up, and it's meant that the rubidium chamber is meant to run at about 100 degrees C. So of course this thing gets hot. All of the rest of the electronics really aren't designed to get that hot, and shouldn't be. Otherwise, it's going to lower the mean time between failure for these things. So, some cooling. The fact that the case, all of the case and all the metalwork gets really hot is just a consequence of that. It's not designed to be like that. In fact, when these are mounted in their original equipment, they're on quite a big board, which has got a big copper area, or big copper surface area, to help keep them cool. And I think, sorry, I was just going to look at that, but basically you don't want this thing getting too hot. You want the physics package getting hot, and there is obviously some thermal coupling. There's a solid metal aluminium block in there that the physics package is attached to. This metal is screwed to that, and therefore you get the inevitable heat transfer. But fundamentally, you want the physics package running at the right temperature, but you want the outer case to be as cool as you can, without getting it to the point where this starts to cause the physics package to have a problem getting hot, or drawing too much current to try and keep the temperature up. So it is a balance, but on the whole, you actually want this cool. Now, this is the standard I worked on. That's been on for a couple of hours now, and you can see that I can put my hand on it, and actually it's about, with just that aluminium plate, it's about lukewarm. Certainly and I've got my hand around the back of it as well, and I'm squeezing that quite tight, and I don't feel compelled to remove my hand or get it out of the way. I could keep that there comfortably forever. It's just warm. So I think the case alone is probably enough. However, I did order a heatsink from eBay, which is that's what it looks like. I bought it on eBay just before I went away there, and when I done this, as I said before in the last video, I didn't have it, so I wanted to fit that, but actually it looks a bit untidy, because it doesn't leave me much space either side, so I need to hack it and modify it a bit, which is what I've done. I've got the hacksaw to it and the file, just made it a bit smaller. That's the original one, that's the modified one. I've just cut a bit off of it, and also just for simplicity, these edges are actually really sharp, because they're a perfect 90-degree cut. It's just where this heatsink has actually been cut in manufacture. This is obviously an extrusion, they've cut it, and if that was on the front of this and it's up on my equipment rack here, and I reach up, and I could very easily cut myself or scrape myself. So the other really simple thing is I've just filed, I don't know if I can get a focus on this, I've just filed the edges round there, so just clean it up, and yeah, so that's that. Now that fits there quite nicely, so I am going to mount this heatsink and put it on there. It doesn't do it any harm. It's going to help take away some of the heat from the base of it. Someone also suggested, which is absolutely right, heatsink compound should be used here on both sides, and I'll do that. And probably because I inverted the front panel, I probably need to clear some of the paint to help that thermal transfer as well. But as I say, the unit itself doesn't really run that hot, so it's not bad at all. The power supply runs nice and cool, and I have run this for a few hours with the lid on, and then opened it up and had a feel around inside, and it's all running pretty cool. Now I have got, just as I don't know if this will work. It's reading 26 degrees. I mean, I'm sure it's a bit hotter than that, to be honest with you. Maybe this thing isn't working so well. Yeah, 26 degrees. And about 30 degrees on the back centigrade. So really not that hot at all. As I say, I think this heatsink is helping it. So I'm going to do that heatsink, put that on there. That was one of the things I wanted to do. The other thing I got asked, which was a good question, is does the 1 pulse per second output work? And we're going to look at that in a second. Because I'd built it, I made assumptions about it, but didn't actually test it. Now, we do get output from it, but I'll show you what that looks like on the scoping because there's a problem, and we're going to try and address that. And then the last question I got asked, quite a lot, I'm not quite sure why, was a lot of people thought that using a small microcontroller to control the LED or to manage the indicator was overkill. And I was going to address that because I want to make a further enhancement, and perhaps I can demonstrate that actually using microcontroller isn't overkill. In fact, the microcontroller I used is very cheap, it's a very low cost device. And you know, a 555 will be fine, but it's just not as flexible. Yeah, so we're going to do a small modification to that just to demonstrate and prove that point, and cut a little bit more code. Okay, so first thing I'm going to do is go and fit this heatsink, and then we'll come back after that. Okay, so I've taken the front panel off. I've cleaned that up. Just used a bit of sandpaper and brought that back to the bare metal. The goal then is to fix the rubidium standard back, but with some heatsink compound in there, so that's easy enough. I've drilled 4 holes into the heatsink and tapped them with M3 screws, and the goal there is to have that mounted on the front like that. I've also cleaned up the front panel a little bit just to make it look a bit nicer. Now, because the rubidium standard actually covers the screws here that are going to hold the heatsink in place, I'm going to use countersunk screws here, and I've countersunk those 4 holes, nice and simple. Now the aluminium is quite thick, so thin, so the countersink probably protrudes a little bit through the bottom. So also in there, I've just very lightly countersunk the holes. So that's it. So I'll put all that together. I won't bother videoing that. I'll get the heatsink compound on there, make sure I keep that clean, get the heatsink fitted, get the rubidium standard, and I'll come right back. Okay, so I've mounted that, put the heatsink on the front there, put the rubidium frequency standard on the back. So that's great. So the next thing we'll look at is the 1 pulse per second, because when I checked it, originally I checked it with a logic probe, which we'll do right now, and then which showed that it worked fine. And then I looked at it, the scope, and saw a different story. So let me just grab the logic probe for a second. Okay, so well, I've got a logic probe here. I'm just going to put that into the 1 pulse per second output so you can see what happens. But it's powered off at the moment, so it's obviously cold, and you'll be able to see the status light. Let's see if I can get that more visible. And the 1 pulse per second does some pretty strange things in the output. So this is, bear in mind, this is through the sync amp, and I haven't really looked at the circuit. We'll look at that in a second. But so we power it up, and you can see that actually it pulses at quite a higher rate than 1 pulse per second. Now I'll just let this warm up to the point where it stabilizes, and then you'll see the effect. So I'll just hold that there. Okay, so you can see that it's locked now, and now you can see the 1 pulse per second. Previously, while it was warming up, it wasn't putting out 1 pulse per second. It was putting out 4 or 5 pulses a second, which is very curious. So what I think we'll do now is just have a quick look on the scope and see what we can see on the output. Okay, so what I've got set up here, This is on the 1 pulse per second output. This is channel 1. Channel 2 I've got connected to the 1 pulse per second signal coming from the RBS directly, so we can see the two correlated. So if I just power it up again, now this is kind of weird thing that we can see as you get this to trigger. You've got this very strange varying data. I'm not sure if that's data, some kind of diagnostics information. It's certainly very weird, and it's where are we? We're at 2 volts of division, so it's about a 3 volt signal coming out of the RBS as well, and that's into, I think, about a 510 ohm load, and we'll look at that signal in a second. So let's just wait for this to normalise, and then we can look at the capture the 1 pulse per second and have a look at the actual output. So I'm actually going to ignore. There we go. So it's now warmed up. And the way I'm going to capture the pulse, because obviously with the spec for the rubidium frequency standard is it's a 1 microsecond pulse that comes out. So obviously you won't necessarily see it. You'll see it blink every now and then. But what I'm going to do is just use single capture mode, and there we go. We can see the output now. What's interesting about this is let's see if we can capture that again. Okay, so this top trace is what's coming out of the video board after the digital processing, and this is the actual signal coming out of the rubidium frequency standard, and you can see that there's a ripple on there. Now what I'm going to try and do is capture that, because I think that's a derivative of the actual clock inside the frequency standard. The main point here being that actually you can see it here very clearly. The main point here being the 1 pulse per second coming out of the rubidium standard isn't very clean, and it needs to be cleaned up. Now this is doing a pretty good job at cleaning it up. You can see this is the actual output. This is 2 volts of division, so it's almost getting to 5 volts there, and that's really nice. The problem we've got on this though is the noise that's on it, and particularly here, this ringing. And I think if we look at that carefully, that switching here correlates to this ringing. So the next thing I thought I would do was actually do a bit of reverse engineering on this board and take a look at the actual circuit to see why that might be happening. So let's just have a look at that. Okay, so to the best I could work out, I didn't put too much effort in, but this is approximately the circuit that's in this thing for the dealing with the horizontal stroke HV sync. This is the input. It goes into a 510 ohm resistor, so that's kind of its nominal impedance. It's DC decoupled through a 10 microfarad electrolytic capacitor, and then there's a very small cap. I'm going to guess 10N, but it could be, I'm not sure exactly what, and a 10K resistor, which is obviously just acting as a little bit of a low pass filter there. Now this is the interesting bit. From the best I can work out, there's 2 diodes, 2 resistors, and then they're tying this negative input of this comparator into effectively a DC load somehow. I'm not sure I completely understand this circuit, but from what I can work out is what this does is the average DC voltage on here plus less about 0.7 of a volt ends up on here, and it's biased towards the positive, but it ends up on here, and it basically self-centers around whatever signal is in here. So you know, if this is a square wave coming in, depending on the Mach space ratio, the DC level, which is like a PWM, the DC level will be in a different place, and this centers around it. And the effect you get is and this is an ultra fast comparator. It's an LT1016 device, 10 nanosecond comparator. So the effect you get here is, regardless of the waveform here, you get some switching. So when we look back at the trace on the scope, we're obviously around that ringing is actually causing this to switch, and we need to do something about that. Then this follows through, I think they've just used a transistor here for convenience, that just inverts it, and then they're driving these through inverters, and then 75 ohms on the output impedance, and there's another 3 of those. So that's really what that circuit looks like. And I think the problem we've got is I've run a single wire over from the Rubidium standard DB9 pin 6 over to this, into this 510 ohm resistor. I'm not sure if that's the right impedance or not, I don't really know, but I think there's some ringing on there. And what I try to do is slug that with some input capacitance just around here. So in effect, strapped a capacitor across here. And I'll show you the effect that had on the scope, and you can see the effect on the input and the output. So let me just get ready to do that and I'll come back. Okay, so what I'm going to try and do is just slug this down by putting a 100N cap just straight across this resistor here, or straight across the input, and we'll see the effect. So that's the current waveform, you can see it there. It's a bit fiddly this, and I can't always get it exactly spot on, but I'll messing about, should get us there. Now it has actually stretched the pulse out, that's okay. And you can see on the bottom trace what it's actually done. It's just smoothed out that ringing, and it's still triggering there. Now, oh, sorry, I just slipped off that. Okay, so this is sort of acting as a bit of a pulse stretcher now, which is actually okay. I'm not that worried about it. The rising edge is still, you know, the important bit there. And actually, as long as it's 1 pulse per second and the period is okay, the frequency is okay, the actual period of the pulse I don't think particularly matters. It certainly doesn't matter to me. So I think it's just as simple as that. What I'm going to do is I'll just come off here again. Yeah, so that's a nice clean square wave. So I think just for simplicity, I'm just going to solder, that resistor is a surface mount 0805 device, so I'm just going to, footprint, so I'm just going to solder 100N straight across that on the board, and just double check that again, make sure that works. Okay, so that's now got 100N across it. The pulse width is about, let's have a look here, is now about 7 or 8 microseconds. I'm okay with that. I'm pretty comfortable. I think that's a quick and easy fix. I could, of course, get into this board and perhaps do something around here to resolve that problem. Maybe just I could set a fixed DC bias on there, and just allow it to flip above. That's probably quite an easy fix as well. But you know what, that'll do absolutely fine. I think that's clean enough. So so that's the 1 pulse per second now working. I'm pretty happy that that's okay. Okay, so probably the question that came up quite a lot, or certainly was asked quite a few times, or you know, people were quite insistent, was, you know, why did I use a microcontroller just to control an LED? Well, the first thing was, my plan was originally to use it for 3 different things. I was going to use it for controlling the LED, for a PWM signal to run the fan, also generate the 1 PPS. Now I didn't need to generate a PWM for the fan because I didn't have a fan that was PWM controllable, so I used one of the DC regulators. And on that point, you know, someone said it was an awful waste of time having, you know, awful waste putting all those buck regulators in there. Well, they cost a couple of dollars each, and I had 10 of them lying around. I needed 3 supply voltages. I'm not putting this into production, so it's not like I have to, you know, count my cost of my bill of materials. So I thought it was a really simple and straightforward solution. Anyway, that's an aside. So, you know, why not a 555? Well, yeah, I could have used a 555, but actually I wanted it to be a bit more flexible than that. And you know, why? So I thought what I'll do is, having looked at this 1 pulse per second problem, what I thought I would do is extend the status LED to actually perform 3 functions. Now that clearly you can't do that with a 555. Maybe 2 functions. No, well, maybe we can, but it will get complicated. So this is what I want to try and achieve. I'm going to have the same behaviour as it is. So when you switch it on now, it blinks until it warms up, and then it comes on solid. And when it's on solid, once it's running, I want the LED to brighten itself, you know, as a peak brightness once a second in synchronization with the 1 pulse per second. Partly, I suppose, as a confidence that it's running, and probably more so to demonstrate the point. Why would you use a microcontroller to do something like this? Well, you know, I'm not sure what else you might think of in your projects, but a microcontroller that costs $1 is really easy to program, really easy to use. It's really a no-brainer. I don't understand why people were so, you know, wound up about the fact that, you know, a microcontroller was making things awfully complicated, whereas you know, I didn't think they were at all. Anyway, so to that end, what I've done, I've made a modification to this schematic, which I'll just try and show you. Now, in the original use of the PIC, you can see I'm just trying to get the right light on here. There we go. I was literally just had the ready signal here, and then the LED on the output. And what I've done is I've added this sort of shaded area, and I've added I've taken a input signal here. I'm feeding it through a Schottky diode straight into the input of a spare input on the microcontroller. And I've put a cap and a resistor to ground, so I'm pulse stretching this, and that will be obvious why it is in the software. But that's the basic circuit. So when I get a positive going pulse here, that will force charge that capacitor. When the pulse disappears, that cap through this resistor will start to discharge, and it'll hold that up for long enough for the software to be able to figure out that it's received a pulse. It being you know, a one microsecond pulse, my original plan was to use interrupts and use edge detect interrupt, and I tried, I have to say, for quite a few hours, not because it took that long, but because I got so frustrated that it wouldn't work that I was determined to make it work. And in the end, I couldn't actually make it work. And we'll look at that in the software. So I ended up in the software polling this input, and as a result of that, because I couldn't detect the edge, it was random, so the chip just couldn't do it fast enough, was what it came down to. The interrupt system on here was just too slow, or the response to the interrupt or the edge change was just too slow. That I just, you know, put in a cap and a resistor and pulse stretch and a diode, and just pulse stretch that signal. So let's have a quick look at the software now and see how that's written, and then I'm going to do the modification, the hardware modification, and implement this thing. So in the original software, I made some modifications. What I've done here, I simply defined the 1 pulse per second input. I've put that on GPIO 4. Now, all that's happening here is it's really simple code. Now, I will say before anyone makes the point that this chip supports edge-triggered interrupts, and you would think that would be ideal. So I originally went down that route. I defined a small interrupt routine. It's on GPIO2. I configured the chip, and the best I could do was get it to randomly detect the edge of the 1 microsecond pulse. It would work maybe 4 in 10 pulses, and it was completely random, and nothing I'd done around the electronics, you know, tweaking it about, really helped. I had the scope on it. I was looking directly on the pin of the microcontroller. It was getting a nice, clean, sharp, rising edge. This is what it was configured for, and it was completely random. And I did spend quite a long time because I just thought that you know, it should work. And you know, having read the microchip documentation, it wasn't that clear, but in edge triggering mode, it should be quick enough. There was parts of the documentation saying in order to, I also tried clocking the timer with the external clock input for the timer 0, and I was getting exactly the same result. Anyway, it got so frustrating in the end that I figured, well, I'm not going to try and solve the problem. So I came up with an alternative solution. As you saw in the schematic, I just stretched the pulse and decided to pole it, and I think the pulse I stretched to about a millisecond, which is more than enough to pick this up. So quick walk through the software then. What does it do? Same as before. If it's ready, if it's not ready, so if this is high, then it just does this original piece of code here. If it is ready, i.e. the frequency standard is ready, is set to low, input, then what I do is I poll the input, see if it's 1, the 1 pulse per second, and if it is 1, I set the LED state variable to 10. Now, all this is, bear in mind this is inside a while loop, so this will come in each time. So each time this comes in here, it will sample that input to check to see if it's got a 1 on it. And if it does, it'll set the LED status to 10. Now, inside here is a really simple state machine. What happens is as simple as this. If the LED state is set to 0, 1 or 2, it will move to the next one. So if LED state is 0, then it'll set the LED state to 1, and the next time it comes back round, LED state will be 1, it'll set it to 2, next time round, LED state is 2, it'll set it back to 0. So it'll keep on cycling 0, 1, 2, 0, 1, 2, 0, 1, 2. And what I'm doing here is I'm turning the LED on for one cycle, for the 0 case, and then I'm switching it off for the first and second case. That means that I'm driving the LED in this condition with a 33% on duty cycle, effectively dimming the LED. Now, if the LED, if the 1 pulse per second input is detected, I set to 1, then I set the LED state to 10, and what happens is it drops into this default case, and each time around the loop it will, because it's not 0, 1, 2, 0, 1 or 2, it's now 10, it will come in here, it will decrement that by 1, so that'll take it to 9, it will turn the LED full on, and it will delay here for 10 milliseconds, and then it will go back around the while loop again, it'll drop back in here, obviously it won't be 0, 1 or 2, it'll be 9, so it'll go to default again, it'll decrement it to 8, the LED state will still be on, it'll delay for another 10 milliseconds. And the effect there is you get the LED comes on full for about 80 milliseconds before it decrements to the point where it gets to 2, it comes back in here, LED state is 2, it drops in here, turns the LED off, LED state is set to 0, and it goes back round and resumes its normal behaviour. And that's it, it's really as simple as that. It's actually quite elegant, and given the chip doesn't have to do anything else, that's a really straightforward piece of code for people to understand. So that's it. Now that's I've programmed that into the chip, so what I'll do now is I'll move the camera, I'll point the camera at the prototype again, and I'll demonstrate this code working. Okay, so this is the chip's now been programmed with the new firmware, which should deal with this this third mode. So that's in its warm-up state, and this is in its standby state. So this is the LED now on. You can see it's a bit dimmer than the original pulsing brightness. Now I've got the this is the 10 meg signal from the 1 pulse per second signal from the rubidium standard, and I'm just going to plug that into here, which is connected here, and this is that diode resistor and cap feeding, creating the pulse stretcher and feeding that into pin 3 of the microcontroller. And once we connect that up, what you should see is, hopefully this will come out on video, but you can see the LED now pulsating 1 pulse per second. That's it, that's the firmware working. It's really simple, quite elegant. So all I need to do now is build this 3-component circuit onto the prototype board inside the video amp enclosure, the one that we built before with the microcontroller on it, and bring a wire back. What I'm going to do, I can just find the diagram. What I'm going to do is I'm going to pick a wire up off of the probably off just the output of one of these buffers here. So I'll just tack a wire on the back of the board from this point here, which I'll run onto the input of the microcontroller. I've got a spare terminal connection there, so I'll go and do that now. Okay, so it's all back together now. I've done the mod inside, tidied up the wiring, screwed it all back together, put the new firmware in there, and you can see that the LED there is blinking. I'm not sure how obvious that is. Let me see if I can get that there, but it's definitely blinking. It's just like a heart. Okay, just to summarise then, the heatsink, it definitely makes a difference. It's lukewarm. I don't know if it's right or wrong to put a heatsink on there. My feeling is it is, and therefore, you know, I've done it. So I'm sure it's not going to do it. Only in use will it tell. The 1 pulse per second, you know, the output of the rubidium isn't fantastic. It needs cleaning up, and it's sort of remarkable coincidence that this video amp happened to have a TTL level sync channel, which I could use to do exactly that. It was a slight modification just to slug the ringing there on the wiring probably. And then the final thing is, you know, this whole thing about microcontroller. Should you use a microcontroller or not? Well, you know, I'll go back to the point. It's really simple to do. They're really cheap. You know, you probably couldn't achieve that third embellishment, shall we say? You know, was it necessary? Probably not. Is it overkill? Maybe. It's quite nice to have a heartbeat on there. The point is, though, having a microcontroller gives you that flexibility. I haven't really had to do much. All right, fair enough. In this instance, I had to add that pulse stretch circuit, the diode, the cap, and the resistor. But other than that, I've managed to do that in software, and it's convenient. If I wanted to do that in using 555s, well, maybe 2 of them, possibly, and you know, some other circuitry. So you know, it's just I think it's a good thing. So, you know, practical, pretty cost effective, and, you know, partly I just wanted to use the microcontroller. So, you know, if people don't like it, what can I do? Okay, so that's it. What I'm going to do, one of the other comments I had, I was very grateful for the fact that the last video made it onto hackaday.com, which was great. One of the comments was people's frustration with just video content and no text content. So I'm going to try and keep a bit more text content and put more of the content that I use up on my blog. So for every video I produce, there is, for those of you who don't know, there is a supporting blog page, and I always put that as the first link, or as the first line of text in the description of the video on YouTube. So you know, just down here there's a link, and that will take you to the blog page that relates to the video. And I always have a blog page for each support for each video to support that video. And on that blog page I have varying amounts of content. Generally I'll put the scans of the drawings I do and that kind of stuff, references to chips that I've talked about or components I've talked about, and so on. This will be no exception. I'll upload the new firmware source code, so that's there. I'll scan in those schematics and so on and so forth.